Hi, I'm Dorien Herremans and I'm very excited to be here today at DMRN. I'll be talking to you about music generation and more specifically about controllable music generation. I'll be going over a range of systems from Morpheus to more recent deep neural networks. I lead the AMAAI lab at Singapore University of Technology and Design, where we have a bunch of nice people working on very cool subjects like audio transcription, cough sound detection, underwater acoustics, singing voice separation, and last but not least, music generation. Now, if we talk about music generation, I think it's important to think back about the history and when this concept was invented. Okay. You might have all heard of the musical dice games, which a lot of people attribute to Mozart. It's actually due to Philipp Kernberger. Kernberger created a concept whereby you have sheet music and each bar is labeled with a number, and you roll dice to create a new composition, meaning you change the order of the different given bars. This is the first idea of having statistics create music for you. About 100 years later, roughly, we encounter Ada Lovelace. Some of you might be familiar with her. She is considered to be the world's first programmer because she worked with Charles Babbage on the difference engine and the analytical engine, which is basically calculators powered by a steam engine. Now, this difference engine had programmable punch cards, and when writing the notes of these cards, Ada wrote, "The engine might compose elaborate and scientific pieces of music of any degree of complexity or extent." So back then, before actual computers as we know them today were built, the idea of using a computer to create music was already there. Now, of course, it wasn't until much later when we actually had electronic computers, another 100 years further in time, when the first musical piece was generated by a computer. This is called the Iliac Suite, and it's a string quartet created by Hiller and Isaacson using a statistical Markov-based and rule-based model. Okay. Now, since then, there's been a lot of research on using different types of methods to create pieces of music. Rule-based methods, simple neural networks, optimization such as genetic algorithms and teacher programming even, factor oracles, variable neighborhood search, and much more. And especially in the last few years, the topic has become increasingly popular, and we've seen interest companies like Google creating music generation systems and a lot of startups appearing in this domain. Now, are we done then? Okay. Do we have a music AI system? Well, do any of you have an app on your phone and you listen to AI music more than you listen to regular music? I assume not. And I think that is due to some of the challenges that are remaining in this field, namely the lack of emotion and long-term structure in the generated music. When I was at Queen Mary doing my postdoc with Prof. Elaine Chu, we worked on this problem and we created the Morpheus system, which is meant to tackle these two challenges. So we modeled emotion using a concept called tonal tension, and we measured long-term structure using a pattern detection algorithm. We put both of these things together in an optimization approach. Let me go over these different points one by one. First of all, we need to be able to measure emotion before we can generate a piece which has emotion. And we chose to use the spiral array, a model of tonality developed by Lane, to capture tension. We defined 3 measures, cloud diameter, momentum, and tensile strain, that allows us to measure how tense a piece is. Here's an example of a famous tense chord called the Tristan chord. It's from the opera Tristan and Isolde, and each time the Tristan character enters the stage, this tense chord is played to create this affiliation with the character. If we put this chord into the spiral array and we compute our 3 metrics, the diameter of the size of this cloud basically, the momentum or the change between fragments, and lastly the difference or the distance between key, we notice that this is an example of a very tense chord. Let's listen to the example. now that we have a way of measuring emotion in the form of tension, we also need a way of measuring how many patterns or long-term structure is in the piece. Now we opted to use the SIA or Kosayatek algorithm by David Meredith. And in Kosayatek, it uses a point set representation whereby y-axis is the pitch, x-axis is the time, and it computes basically repetitions of the same pattern. It can be transposed, so it finds any possible transposed pieces of music. The Bach prelude example here shows that Kosayatek finds most prominently the red and the green pattern, which you can also hear in the music. Right, so how does Morpheus put this together? So we start from a template piece. We erase all of the pitches, but we keep the durations. Then we try to find new pitches, starting from completely random pitches. Okay? And our objective will be to match the tension of the original piece. If the user wants, they can change the tension as well. And then we'll hard constrain the detected patterns. So note, we don't hard constrain how the patterns look, but we hard constrain whenever they return, meaning that you can fill up the pattern with new content, but it will be repeated. So it forces a longer term structure. So how does Morpheus output sound? First, as a template, I gave it this very famous Bach piece. You're all familiar with this. And then first what we did was we replaced all the pitches with random pitches, but we constrained the pattern. So there's some repetition in there, but it's still very random sounding. Right. Then we let Morpheus optimize this so to match the tension. So quite interesting, and I think it's because it violates our expectations in ways that we might not expect, but then it complies to our expectations in different parts. So it's a very interesting experience. If you want to listen to more pieces generated by Morpheus, just visit the QR code link there and it'll show you a bunch of other very interesting performances. What we did especially for Beethoven's 250th birthday, which is tomorrow, we generated a new For Elise, which gave us a very interesting result. I have actually displayed the pattern detection output here. So you can see that there's a lot of patterns that span across the entire piece, these long red lines. That means that in For Elise, for instance, the original it comes back many, many times. So the pattern detection actually manages to capture that. Okay. The result, I'll show you an excerpt of the result. So really an excellent job by Elaine performing this piece. If you want to listen to the full piece, which is premiering digitally today, you can visit the link behind the QR code and you can watch the whole performance. Now our lab in the current days wanted to take this one step further, and we wanted to be able to learn the actual style of a data set of pieces and still control this generation. Okay. Can we still map emotion using deep neural networks, and can we bring in these earworms or these long-term structures in the music? And we have a few projects running to try to do this. First of all, we're trying to build models that can disentangle tension as we defined it with Morpheus. So this will allow us to steer the generation in terms of tension. One of the students I work with, Rigwo, has actually developed this variational autoencoder that is trained to learn what these tension metrics are and disentangle them in the latent space. Okay. By doing this, we can do transformations in this latent space, and we can generate music from scratch and then transform the tension of the generated piece so that it changes slightly. Okay. Ray worked with a piano roll that had 2 monophonic tracks, melody and bass, and he used the MIDI minor. He actually developed the MIDI minor library that can do the tension calculation and track separation in Python. Okay. Here's an example of the output. So first of all, we just generate seed from scratch. So the idea is that we can use this seed music that we generated and transform the tension by these transformations in the latent space. So one thing we could do is we can make the tension metric, increase the tension in the piece. Or we can decrease the tension in the piece. So the cool thing is that using this, we can create variations on the seed and put them all together in a larger song. Now, we take this one step further, and we've developed MusicFaderNets. And FaderNets is built on the concept that we can control high-level features through bridged low-level features. In FaderNet, which was developed by my RA, Hao Tan, we wanted to mimic the effect of having faders in a music production studio. So our low-level faders here are things like rhythmic density and note density. And based on this, we can actually go to higher level features, such as arousal, and we can try to learn the settings for rhythmic and note density to control these higher level features like arousal. We used a Gaussian mixture variational autoencoder, which consists of 3 parts, basically. We have the typical reconstruction module. There'll be a reconstruction loss, so we try to reconstruct the music. Then we also have a discriminator model, which tries to predict the labels in low dimensional space. So it enforces us to do latent space disentanglement. And then we have a third component, which is cluster inference, and that basically is trying to infer clusters of high-level settings or the high-level features like high arousal, medium arousal, etc. Okay. So these 3 components will make up our final loss function. Okay. That means we trained this on the Yamaha e-competition dataset and the VG MIDI dataset, which gave us 1% labeled data for arousal, the higher level feature. That means that this second component of the system is actually semi-supervised learning. Okay. All right. So here is an original fragment. That we then have transformed, so an original fragment generated by the system, that we can then transform from low to high arousal throughout the song. So again, we can do these transformations of the generated music or of existing music even through the latent space, which is pretty cool. You can go to the website of MusicFaderNets. All the code is available, and there's a bunch of examples where you can examine if the sliders really work So all of these systems are great in terms of making short fragments with steerable tension or arousal. Now, we wanted to take it one step further and make actual longer music which controlled valence. Valence is sort of the positivity or negativity in the music. So my postdoc, Dimos Makris, created this lead sheet generator, which is controllable through a unique encoding representation. It's event-based. The user only feeds it time signature valence, like your controllable parameters, key, etc. And it's treated as a neural machine translation task. So it basically translates the conditions into actual lead sheet events. For instance, the encoding will look a little bit like this. In the encoder, the user inputs time signature, density, etc. And you just feed it an event-based representation based on these features, and it gets decoded by the system or translated into chords, duration, and notes. Okay, so basically into lead sheet. It is ready for sequence-to-sequence architecture. So what we did is first we tried a transformer, which gave us pretty good results. Here's a fragment of a low valence piece generated by a 4-layer transformer network. It's not bad. It sounds pretty sad, mellow. We generated a similar piece with similar conditions using an LSTM, multi-layer LSTM network. It's not bad. It needs some, I think it misses some cadences. And in general, I like the transformer example better because it has some clearly repeated structures, such as the syncopation here, which comes back later here. Okay. So we're still testing these systems and we're busy in the process of writing them down somewhere. So keep an eye out on our lab website. Finally, we have somebody working on dedicated hierarchical RNNs to really enforce structure that comes back throughout the piece. Okay. Nicolas is working on hierarchical RNNs, which are based on the sample RNN, which you often see with waveforms. And the hierarchical RNN basically looks at the input in a sort of dilated way. So it looks back, different layers, different tiers, look back further in time or not. It's an autoregressive approach, also with an event-based representation. And we look through, or we use the data of hook theory or the theory tab database to generate and train the network in different genres. For instance, here is an example of a piece generated that was trained on electronic music. So this is particularly well suited for very repetitive music or structured music that has verses and choruses coming back. It can deal with that larger structure. It can properly deal with meter, finding and predicting accurately bar events, etc. Right, so the future of music generation, I'd say it's here. Look at all these systems that have been developed the last few years. But there's still some challenges like proper controllable music generation, embedding in emotion and structure. And our lab at SUTD is really exploring these different approaches to try and tackle these last remaining challenges to bring music generation out for widespread usage. If you have any questions, I'd be very happy to answer them. Thank you for your attention.